Okay, so here again, once again, if I'm going to have radial and thrust force, in that case, it's not just a pure not pure thrust. And we will see that the equation now for the P is going to be extended to have the VXR multiplied by the YT. So P is going to be equivalent load, the V is going to be rotation factor as defined, the R is going to be applied radial load, the T is going to be applied thrust load, the X is going to be radial factor, and the Y is going to be thrust factor. So if I get to get the value for radial and thrust force, we need to find the value for the Y and the X. So usually you can simply suggest that the X and the Y at the beginning to be suggested. You can see in this table saying that the X always going to be 0.56 for all value of the Y. The Y value are going to be variable, depend on some of the parameters like the value for the thrust force divided by the static load, okay, or the T over C of. So once again, we said that um, the X and Y vary with the specific design of the bearing and with the magnitude of the thrust load relative to the radial load. Now, for relatively small thrust, the X can be used as 1 at the beginning and Y is going to be equal to 0 for the pure radial loads, as you remember. The presence of a difficulty on the bearing selection because the value of the CO is not known until we're going to select a bearing. Therefore, the simple trial and error method is going to be applied. So the steps of the calculation start first with assuming that the value of the Y from the table 414, we can use the value for the Y to be 1.5, is going to be reasonable and be about the middle range of the possible value. So we can compute the p-value by using the equation of the VXR plus YT, where the X is going to be 0.56. Then compute the required basic dynamic load C from the equation 14.1 or the 14.3 or the 14.4, and then select the candidate bearings having the value of the C at least equal to the required value. A little bit more is going to be okay. For the selected bearings, determine the CO, you compute the T over CO, and then you are going to find the value of the E from the table 14.5. And if the T over R value is going to be more than the E, then simply just compute the Y from the table 14.5 and then repeat the process if the Y value is going to be different from the assumed one in the step number 1 and repeat the process. If it's going to be the same, select a new value for the Y and redo the calculation until you're going to have the condition of the TR is going to be less than E. Then if yes, use the equation 14.5 to compute the value for the P and proceed for the pure radial load. So that's just to remind you what the equation 14.3 you are talking about. However, we're going to have the example 14.4, which is similar to the question we have here, the question number 4. The difference is that the load is going to be different based on your student number. The thrust load is going to be different based on your student number, the RPM value, the life in hour, okay, and the diameter is going to be 94 ohm. So in general, in the tutorial, the class tutorial, we are working on your own numbers, not going to repeat this question. We just following the steps. So once again, we have we need to select a bearing where the radial load is 8,228 and the thrust load is 3,002 Newton and the shaft is rotated at 120.4 radian per second or the 1,150 RPM. Well, I can see that the value is not quite different from the one you had in your example. So you just need to first do this one and then you can do your example question. So the design life of 20,000 hours is going to be desired, and the minimum acceptable diameter for the shaft is 78.74 millimeters. Now, we're going to start with the steps one by one. So the solution starts with step number one, assume the value for the y and x. Second, calculate the p-value. Third, calculate the basic dynamic rating C from the equation 14 and 3. Now we know the life, so we can calculate how many revolutions is going to be used there. So 30,000 hours multiplied by 600 RPM multiplied by 60 minutes per hour, and we'll come to the solution that the answer is going to be 1/8 multiplied by 10 up to 9 revolution. Now calculate the C with the LD of the 1.08 multiplied by 10 up to 9 divided by 1 million, and this will make it 1080 up to 4.333 multiplied by the PD of 8,000, the 9,113 Newton. And we'll come to the answer of, okay, the answer now is going to be equal to 93,541. Now we're going to go to the table in step number 4, table 14.3, and we may choose the 6,316. Now, why we choose that? We're going to locate for a candidate based on the C value of the 91,000. So we said that the diameter should be more than 78.8 millimeters. So we're going to look here. That's 75, that's 80. I don't need to go for the next table, which is going to be 85. So let's stay at the 80, which is barely equal to the 78.8. And that's the minimum diameter we have. So 124, yes, it's more than the value of 93.5. Okay. And then I will say that the candidate bearing is going to be 6,316 for the number of the bearing, which can have all these specifications. But till this moment, I cannot say that this is my bearing. I'm going to continue with the work. So the 6,316 had the bore value of 80 millimeters, which is well suited for this application. Now, next step, I need to find the value for the static C, or the CO. So here the CO is equal to 86.5 kilonewton. And I'm going to use that for my next step, which is step number 6. So step number 5 is, well, actually, I should do that as animation. Anyway, step number 5 for the 6,316, the CO is 86.5 kilonewton. So the T over CO is going to be equal to 0.034. From the table 14.5, we're going to find the E. So you can see that the E I'm going to find is based on the value of the T over CO here. Let's locate between the 0.028 and the 0.056. And if I get to make an interpolation for that, I will find the value of the E, like this one. So it's going to be equal to 0.23, which is less than the value of the T over CO. And thus, I need to redo the calculation with the new Y value. Remember the first Y we choose was 1.5. So again, to repeat the process by finding the Y, okay, finding the Y, because the TR is more than the T over R is more than the E. So again, to repeat the process, find the Y by doing the interpolation between these two values. Okay, these are the steps, and I found it to be equal to 1.77. So now I will go to the step number 9. Based on the Y of 1.77, we're going to recompute everything starting for the P. So I'm going to apply the equation for the P, the same X value, and I'm going to start to find that the P is equal to 105,023 Newton. Now recalculate the C, the LD is going to be the same, so the C now is going to be increasing to 107,669.5 Newton. So now I know the new C, and I'm going to continue to do my calculation. Basically, I can find that this value is less than 124,000 Newton, which is the C for the model 6,318. And that's it. That means that the value of the C here for the bearing 6,316 is still satisfactory. Therefore, we can specify that the bearing for this application can be used. If the C value is going to be more than the C for the bearing, then simply we need to select a new bearing which have higher value of the C, of course, and larger diameter, and repeat the calculation from the step number 5. So the next question we're going to do is going to be for the tethered roller bearing.